was going through the questions and doubts that some of you have mailed me. In order to access that, I have typed in the website address www.topperlearning.com, which in itself has a lot of useful information in its domain name. One such information is the domain name .com, which tells us this is a profitable site. We also have FAQ, which gives us the location of the page within the site. Finally, we have .php, which tells us the computer language in which the page is written. Does such a system of nomenclature exist for chemical elements as well? Get ready to find out. Hi, it's great to have you with me for another scientific foray into chemistry. On today's show, we will discuss how to name elements with atomic numbers greater than 100. We'll also learn how electronic configurations of elements are related to the periodic table. Then we will move on to sample exam questions and special tips in exam decoded. How many elements do you think there are in the world? Well, as each one gets discovered, it is given a specific name and configuration, much like the domain names we just saw. Traditionally, newly discovered elements were named by their discoverer. They were then ratified by the International Union of Pure and Applied Chemistry, or IUPAC. But over time, this system seemed to develop loopholes. Certain scientists were so eager to stake claim on newly discovered elements that they declared their results without supporting it with reliable data. One such controversy occurred in the mid-1960s with a newly discovered element having the atomic number 104. Both the Soviets and the Americans claimed to have discovered it first. While the Soviets named it Kurchatovium, the Americans called it Rutherfordium. In order to avoid such conflicts, the IUPAC framed fresh guidelines to name all new elements whose complete data had not been collected. The nomenclature would be derived from the digits of the atomic number. The numerical roots for 0 and numbers 1 to 9 are as shown in table. The first letter is the abbreviation representing the name of the root. For example, the root assigned for 0 is nil and its abbreviated form is N. These roots are put together in the order of digits of the atomic number. This becomes the temporary or interim name of the element. Let's try naming an element with atomic number 119. According to our table, the roots for 119 will be an and ENN respectively. Finally, EM is added at the end. So the temporary name for this element would be ananinium. And what would its chemical symbol be? The first letter is written as a capital letter. The symbol consists of 3 letters derived from the roots. Hence, for ananinium, the symbol will be UUE. I would strongly advise you to learn up the table of roots based on atomic numbers, as examiners love to play the name game, the interim name game that is. Does the IUPAC nomenclature remind you of what we discussed right in the beginning? That's right. Just as every part of an internet address gives us crucial information about a particular web page, each IUPAC name provides you with a wealth of facts about its elements. Take a look at the table. You will see that the permanent name usually reflects the place of occurrence. These names are allotted in consultation with representatives of countries in IUPAC. Sometimes an element is also named after distinguished scientists as a tribute. Roentgenium has been named after Wilhelm Conrad Roentgen, who discovered X-rays and won the Nobel Prize. And speaking of Nobel Prizes, guess who the element nobelium is named after? That's right, Alfred Nobel. As we have just learned, atomic numbers are essential for naming newly discovered elements. Atomic numbers indicate the number of electrons that an element has, which in turn gives us an idea of the properties of that element. As you all know, in an atom, electrons are distributed in shells and subshells. This distribution is called electronic configuration. Now let's look at a table which will help you recollect the number of electrons in each shell and subshell. Each s orbital has 2 electrons, p orbital has 6 electrons, d orbital has 10, and f orbital has 14 electrons. These electrons arrange themselves in a very specific order, and though it may seem a little difficult to learn, if you listen closely to my special rules, it will be less daunting. The specific order in which electrons fill up orbitals follow the n plus L rule, where n is the shell number and L is the subshell. Electrons are filled in the lower energy levels first, and if 2 orbitals have the same energy level, then the one with the lower n value is filled first. Take a refresher look at the sequence of filling electrons in orbitals: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d. Learn this order well because it is key to understanding the relationship between configurations and the periodic table, not to mention providing speedy solutions to exam questions. Remember the name game I had told you about earlier? Let's play a round as I go in for a short break. Give the atomic number of an element whose interim name is Unpentium. I'll be back after this brief interlude. Till then, keep thinking. I hope you spent the break finding out the atomic number for Unpentium. For the solution, you need to use the IUPAC system of roots. The root Un stands for 1 and the root Pent stands for 5. So, Unpentium implies an atomic number of 115. Easy, wasn't it? Now let's take a look at the periodic table and see how electronic configurations change as we move along its columns and rows. First, the groups. As we move down, the number of shells keeps adding by 1. Another interesting observation is that no matter how many shells are present, the outermost shells of all the elements within a group have the same number of valence electrons. For example, all the elements of group 1 would have an ns1 configuration. Can you think of how this affects the behavior of these elements? Well, similar electronic configurations as seen down a group mean that the elements have similar properties. What other information can we gain from configurations? By looking at the shell number for the ultimate shell, we can get the period to which the element belongs. This brings us to what happens along the horizontal rows of the periodic table. In an atom, the electrons are distributed as follows: 2 in the first shell, 8 in the second shell, 18 in the third shell, and 32 in the fourth. A similar distribution is seen of elements in the periodic table. The first period, where n is equal to 1, starts with the filling of the lowest level, 1s. As you know, it has two elements, hydrogen and helium. Let's move to the second period now. This has 8 elements which progress from a 2s to a 2p configuration. The first two elements have electrons filling the 2s orbital. As we move along the period, the 2p orbital of the next 6 elements get filled up one by one. Finally, we get the stable configuration at the 8th element, which is neon. The third period has 8 elements from sodium to argon. As n is equal to 3, the outermost electron for the first two elements enters a 3s orbital. In the remaining 6 elements, the valence electron enters the 3p orbital. Now pay close attention, because in the fourth period, the configuration begins to get a bit more complex. This period starts at potassium and has n is equal to 4. So, the first two elements' valence electrons fill up the 4s orbital. But now, instead of going directly to 4p, the electrons first fill up 3d. Why does this happen? Just recall the n plus L sequence of electron buildup we studied a little earlier. The transition occurs at scandium, and until zinc, it is the 3d orbital that gets filled rather than 4p. These elements are therefore called the 3d transition series elements. After zinc, the electrons begin to fill up 4p, and the period ends at the noble gas krypton with this orbital completely filled. So, we can say that the fourth period has 18 elements, and the orbitals used are 4s with 2 elements, 3d with 10 elements, and 4p with 6 elements. In period 5, we observe a similar phenomenon when the 5s orbital fills up before 4d. So after atomic number 38, the 4d transition series of 10 elements starts from yttrium to cadmium. The fifth period ends at xenon with the filling up of the 5p orbital. All in all, this period has 18 elements, and the orbitals used are 5s with 2 elements, 4d with 10 elements, and 5p with 6 elements. Now, just as the fourth and fifth periods show similarities in the way electrons fill their orbitals, the sixth and seventh periods are also similar. They both have 32 elements each and show a similar break-in sequence after the 5d and 6d elements respectively. There are 14 elements each for 4f and 5f orbitals, which are placed separately in 2 rows below the periodic table as shown. In the sixth period, electrons follow the sequence 6s, 4f, 5d and 6p. After lanthanum, the 14 4f elements from cerium to lutetium are called lanthanoids. In the seventh period, electrons fill up according to 7s, 5f, 6d and 7p. The 5f series starts from thorium to Lawrencian and is called actinoids. Some of you may be wondering how you will remember all this confusing information for the exams. Don't worry, because I've got a simplified version of the periodic table that will make your job easier. Take a look at this pared down table. Just draw out a similar one at home to use while doing practice tests. By the time the exams come around, the order will be as familiar as the back of your hand and you will sail right through the trickiest questions. Speaking of which, I have a student calling in with just such a tricky question.
When we move down a group, a shell is added, but in spite of that, the fourth and fifth period both have 18 elements. I'm unclear about why there is no increase.
This is a good question and quite popular with the examiners too. First, let's see the value of n. The fourth period has 18 elements and the orbitals used are 4s with 2 elements, 3d with 10 elements and 4p with 6 elements. For the fifth period, we have n is equal to 5, which means it will have s, p, d and f orbitals. The 5f orbitals will not be filled until 7s is filled in the seventh period. So, in the case of elements in the fifth period, only 5s, 5p and 4d are filled. That means 2 elements for 5s, 6 elements for 5p and 10 elements for 4d bring the total to 18 elements. Knowing an element's group and period informs you about its configuration. Is the opposite true as well? Yes, it is. For example, for potassium with atomic number 19, the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. The outermost shell is 4, so the period is 4. On the other hand, the group number of an element is equal to the number of valence electrons. In the given electronic configuration of potassium, the number of valence electrons is equal to 1, implying it belongs to group 1. It's time for a well-earned break now. But do return, because next we will see how to translate what we have just learned into top exam scores. Welcome back. Today we have learnt about the nomenclature of elements with atomic numbers greater than 100. We have shed light on the IUPAC nomenclature using roots defined by IUPAC. We have also understood the correlation between electronic configuration and the periodic position of elements. That is, period numbers are defined by the number of shells . I hope this revision has placed you at the correct energy level to take on the exams. If yes, then join me for Exam Decoded. What are the most frequently asked exam questions? How can I optimize my preparation? What special information do I need to keep in mind to score well? If these echo your exam worries, then stress no more, because Exam Decoded is here to lighten your load. Before I set about giving you handy tips, let's see how well you have understood today's topic. How about a quick rapid fire? First, the rules. I will ask you 5 questions. You will need to respond to each in under 5 seconds. Give yourself a mark for every correct answer and We will tally the scores at the end of the round. Let's kick it off with the first question. What is the IUPAC name for an element with atomic number 114? A. Ununquardium, B. Ununpentium, C. Ununennium, D. Nobelium. The correct answer is option A, Ununquardium, according to the 3 roots defined by IUPAC. Second question. Is this true or false? The symbol UNO stands for an element with an atomic number of 108. This is true. UNO represents the first 3 letters of the IUPAC roots for 108. 1, un, 0, nil, and 8, oct. Question number 3. True or false? The element with electronic configuration 1s2, 2s2, 2p6, 3s1 belongs to the 3rd period. This is true. Here is your second last question. The element with the electronic configuration 1s2, 2s2, 2p6, 3s2 belongs to the 2nd group. True or false? The correct answer is true because it has 2 electrons in the outermost shell. Your last question is, state if this is true or false. Transition elements are present in the 4th period. The final answer is true. The 4th period contains the 3D transition series. Let's see how you have fared. To all the perfect scorers out there, well done. You are today's high flyer. If you have scored 4 or 3, you are an achiever. You are a learner if you have scored anything less, and you will have to step up your preparations to earn those perfect scores. Fortunately, we have just the thing to help you out. Log on to www.topperlearning.com to find many more practice tests. Now that you have a better perspective on how well you know this topic, let me tell you more about the question papers you can expect. Today's lesson on nomenclature and electronic configurations is part of the unit Classification of Elements and Periodicity in Properties that accounts for 4 marks out of 70. Since it's important, don't neglect it because it's a great topic to score quick marks in. That's because probable questions from this topic can be very short answer type of 1 mark or short answer type of 2 marks. Most typically, they summon your ability to configure conceptual information into easy solutions. You could be asked, why are the lanthanides renamed as lanthanoids? This is an easy type question for 2 marks. Here is another sample modeled along the lines of very frequently asked questions for 2 marks. Predict the atomic number of the element whose symbol is UNE. In order to answer this, you must be familiar with the IUPAC rules for interim names. As you know, U stands for 1, N stands for 0, and E stands for 9. So, it is easy to see that the atomic number of the element is 109. It's a simple answer, and each step of the answer accounts for half a mark. So I shouldn't come to know that you haven't got full marks if you get this question in your exams. How about some more inside information on what to expect in the exams? Time to meet today's expert.
It is very important for you to understand the exact order and reason for filling up of orbitals. You must clearly know the explanation for the position of transition metal, lanthanoids and actinoids in the periodic table. Normally the questions are framed like, in terms of period and group, how would you locate the element with given atomic number? Or on the basis of quantum numbers, you may be asked to justify the maximum number of elements in a particular period. Say for example, why 6 periods should have 32 elements, neither one more nor one less.
Well, we have reached the penultimate shell of today's episode on nomenclature and configurations. You know, Shakespeare once said, "What is in a name?" Well, in chemistry, naming and assigning configurations is the gateway to a world of unknown elements, a world that you now have special access to. So use this advantage well, study hard, and strive to become a topper.